let's look at some counting problems. A hacker wants to guess a 4-digit personal identification number. How many possible 4-digit pins are there if the pin must start with a 1 or a 5, repetitions are not allowed, or repetitions are allowed? So we have 3 different possibilities, and they are different. We're going to treat them differently as if they were completely new problems, because they are. But let's take this word digit. A digit is one of the single numbers 0 through 9. So when we talk about a 4-digit pin, we're looking at these numbers and taking 4 of them as our personal identification number. You likely have this for credit cards or debit cards or ATM machines, that kind of thing. How many digits do we have? If we count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have 10 total digits to choose from. If we look at the first scenario, where the digit must start with a 1 or a 5, I'm going to create 4 blanks. Each one of these is to represent how many choices I have for each of the numbers in that pin. So first digit, how many choices? Second digit, third digit, fourth digit, how many choices? In the first question, we have the pin must start with a 1 or a 5. So I have to start my pin with a 1 or a 5. How many choices do I have? I have 2 choices for that first digit, a 1 or a 5. That's all I can have. For the second digit, how many choices do I have? Well, there's no other restriction given here. It just says the pin must start with a 1 or a 5. So I could have any of the 10 digits for the second slot, any of the 10 digits for the third, and any of the 10 digits for the fourth. And if we multiply these together, 2 times 10 times 10 times 10 will give us 2,000 different pins that we could have. In the next example, repetitions are not allowed. What does that mean? Well, I have my 4 numbers, but repetitions are not allowed means I cannot have a pin with 2 of the same number in it. Repetitions are not allowed. I'm not allowed to repeat a digit. How many choices for the first digit do we have? We have 10 total digits, so we have 10 choices. I choose a number for the first digit, so 1 number is gone. How many digits do I now have for the second place? Well, if I've chosen one for the first digit, I cannot use that one, so I only have 9 digits left. We could run an example here if I started out with a 5 in the first spot. So looking at an actual pin, totally made up here. 5 in the first spot. If I'm looking for a number in the second spot, I cannot pick 5 again. I can pick any other number, 6. So I have 10 total choices in the first spot. I can't pick 5, so I have 9 in the second. In the third spot, I cannot pick 5 and I cannot pick 6, so I have 8 choices. And then in the last spot, I cannot pick 5, I cannot pick 6, and I cannot pick 1, so I have 7 choices in that third spot, and then we can pick a number, whatever it is. So this is a way that we can talk about counting and repetitions are not allowed. If we multiply these together, 10 times 9 times 8 times 7 is 5,040. But we can also use permutations here. When we do not repeat things and we are arranging, the order is important. 1, 2, 3, 4 is not the same pin as 4, 3, 2, 1 because we enter them differently. This is a permutation, so we can think about it as a 10p4. We've got 10 digits and we're choosing 4 of them. And if we run the formula for a permutation, 10 times 9 times 8 times 7 times 6 factorial, because 10 minus 4 will give me 6 factorial. I can cancel the 6 factorials, and then you can see that 10 times 9 times 8 times 7 right there. Permutation. We'll get that same answer. And then how about the last part for this problem? Repetitions are allowed. So this time we could have a pin that's 8888. All 4 8s. There's nothing wrong with that in this scenario. So let's put our 4 spots down. How many choices do we have for the first spot? We have 10. How many for the second? It doesn't matter. We can repeat. We have 10 more. 10 choices for the second spot. For the third spot, 10. For the fourth spot, 10. Multiply these together and we get 10,000. Okay. Now, let's talk about racing. Here we have some swimmers. They're going to a swim meet. They're going to race. If you've ever participated in racing sports, or if you watch them, whether it's a car race, a swim meet, a track race, a horse race, all of these different races have 2 stages generally. The first stage is a qualifying race. The top so many racers after the qualifying race will go on to the winning race. So for a qualifying race, there's some predetermined number that if they win the first race, they go on to the second race and they race for the actual award. We call this a qualifying race. We could say something like the top 8 swimmers will go on to the trophy round, or if we're in the Olympics, the medal round, for example. So there will be one race beforehand. In a qualifying race, if you come in first, or in this case, in my example, 8th, it doesn't matter. It doesn't matter in what order you come as long as you're the top in that group, top 8. Because then in the winning race or the medal race, that's when the order matters. Coming in first, you get a gold. Coming in 4th, you don't get a medal. So for the winning race, the order matters. I know I have 8 swimmers here, and the problem in your notes talk about how many different results could there be for the 8 swimmers, but I want you to think about instead a slightly different scenario dealing with the qualifying. So you can write this in your scratch off to the side. We can look at this example. If 20 swimmers compete in a qualifying round, how many ways can 8 swimmers qualify? Here, since we're doing a qualifying round and coming in first versus coming in 3rd versus coming in 8th does not matter, we have an order does not matter situation. This is a combination. So we could do 20 combination 8, and I'm going to pull up a little Excel window here to do this combination. So combination, COMBIN, 20, and we're going to take 8 of them, and we get 125,970. 125,970 different ways we can have 8 swimmers out of 20 qualify for the next round. Okay, now we've got our 8 swimmers. How many different ways can they finish the race? Here are our 8 racers. How many different results can they be for those 8 swimmers? We can show our work using the fundamental counting principle. So how many choices for first place? How many for second place? For 3rd, 4th, 5th, 6th, 7th, and last place? Well, for the first place, we have 8 swimmers. We have 8 total possibilities for coming in first. Someone comes in first, and then we have 7 choices for coming in second. Someone comes in second, so we have 6 for the third. And I think you might be able to see that pattern. Every time we commit to a place, we have one fewer person to place for the next one. So 5, 4, 3, 2, 1. Fundamental counting principle, the multiplication axiom. Remember, these words are interchangeable in statistics and probability. These multiplied together also equal 8 factorial because we're multiplying 8 all the way down to 1. Let's put this one in on our computer or in Excel or Google. We cannot use the exclamation point in Excel or Google because that means something different to the spreadsheet program. They do have a factorial function. So at fact, parentheses, we're going to do 8 factorial. So we'll put that in. 40,320 gives us 8 factorial. Comparing this to, for example, our scientific calculator that's built in here, we can do 8 factorial and we get that same number, 40,320. Let's try the next problem. How many permutations of letters can be made from the word probability? Permutations are orders, but we have to be careful here. We have same letters showing up, so we have 2 B's and 2 I's, meaning that if we were to switch the B's, that gives us the same word. It's not different. So we need to divide out the extra, the repeats that we would get. This is an example of the permutation rule where some objects are the same. And so that's what we're going to look at in this problem number 3. How many permutations of letters can be made from the word probability? So if we count the number of letters in the word probability, there are 11 total letters. 2 B's and 2 I's. It's important that we note the repetition that happens because that's how we use the formula. So the permutation with same objects, we're arranging all 11 of them, but we're going to divide out however many repeats we have. So we have 2 B's, so 2 factorial on the B's, 2 factorial on the I's. And if we multiply this out, 2 factorial times 2 factorial will just give us 4. So we can pull up our calculator and say 11 factorial, really big number, 39,916,800, divided by 4, and we get down to 9,979,200. And in the next part of our lesson, we'll look at more of these permutations and combinations.